Hey guys, we're back for another model. Ready? Let's do it. Let's go. We've got another model for the kidney. This is a close-up on the renal cortex, and we're going to be looking at a nephron. We're going to be looking at renal tubules. We're going to be looking at blood vessels as well. This is our medulla down here. And let's start out with an arcuate artery right here. Here's an interlobar artery, arcuate artery. We've got a corticoradiate or interlobular artery right here. Of course, this is the one that your teacher would probably ask on the exam just to try and be sneaky. But they're both corticoradiate or interlobular arteries. We come up, we get an afferent arteriole, which leads us into a set of glomerular capillaries. This is the glomerulus right here. This is where blood filtration takes place. Fluid is pushed out of these capillaries into the lumen of the glomerular capsule. And this is the parietal layer of it right here. And that fluid that results from filtration is appropriately called filtrate. Yeah. And the filtrate flows onward into this nearby twisty little tube, the proximal convoluted tubule. And we're going to stop here for a second, but let's go back to the glomerular capsule and the glomerulus. Not all the blood gets filtered. Maybe 20% of the fluid and small solutes end up becoming part of the filtrate. So the rest of the blood has got to leave these capillaries, and it goes through the efferent arteriole. That's the sound it makes. And then it gets into the paratubular capillaries, which are these guys right here. And notice how the paratubular capillary is right next to the proximal convoluted tubule. And this is awesomely important because when we have the filtrate flowing, right here, the filtrate is flowing, the filtrate has good stuff in it. Okay, when we do filtration, the only criterion for filtration that we're really worried about is size. Water and small stuff get filtered. So things like glucose, amino acids, vitamins, ions, stuff that we might want to keep ends up in the filtrate and we don't want to urinate it away. So we want to get it back. So what we do is we take it out of the filtrate and we stick it back into the blood, and these guys are right next to each other. So we can do some active transport and some diffusion and a whole host of transport processes to get glucose in here back into the blood. We're going to reabsorb sodium as well. When we reabsorb sodium, what's going to naturally follow but water? And that's good because if you're an average male, you're going to filter about 180 liters a day. That's about how much filtrate you make in 24 hours. Now, obviously, you cannot pee that much, maybe 1.5 liters, depending on how much drinking of water or other liquids you're doing. Anyway, I gotta stop rambling on these. Also, the other process that happens is when we do the filtration here, we don't filter every bad thing. We end up with bad stuff in the blood. And the bad stuff has got to be taken out of the blood and stuck into the filtrate. So we do that, and that process happens here as well. It's called secretion. So good stuff that gets filtered, we want to get it back. That's called reabsorption. Bad stuff that wasn't filtered, we want to get rid of it. That's called secretion. And those are the two integral processes to making urine. Because if we couldn't do reabsorption, we would pee away all our glucose. And if you're peeing away glucose, that's a bad thing. If you're peeing away glucose, maybe you're diabetic, or it's November 1st and you're a 10-year-old kid. Think about that one. Anyway, let's keep going. We got the proximal convoluted tubule, which is convoluted, which lets us pack a lot of surface area. And it's got microvilli. We saw them on another video. And we keep going, and we get to the loop of Henle, named after Mr. Henle. No, not Mr. Loop. And the loop of Henle has a descending and an ascending limb, and its structure is going to let it set the stage for some urine concentration. I know you guys are mad that I'm not going to get into the exact mechanism of that right now. You're probably watching this and you're furious and cursing, but hey, whatever. After we go through the loop of Henle, and by the way, we got a set of blood vessels around the loop of Henle that interact with it. These blood vessels down here, because they're kind of straight-ish, use your imagination, they're called the vasa recta. And anyway, back to the loop of Henle. The loop of Henle comes up, and we get to the distal convoluted tubule. He's farther along our path of flow here, so he's distal. He's still convoluted. He's not as convoluted as the proximal one. He doesn't have as many microvilli because he doesn't do as much reabsorption secretion. I like to think of this is where you fine-tune it. It's in the proximal tube where you do your bulk. You get all as much as you can, get all your glucose back. Lots of sodium, water, whatever. In the DCT, the distal convoluted tubule, your body is going to figure out, what do you need? Do I need a little bit more potassium to keep? Do I need a little sodium to get rid of? And you kind of do your adjustment here. By the time you're done with the distal convoluted tubule, we end up in this tube called the collecting duct. And the collecting duct will now have urine in it. We see several distal convoluted tubules emptying into one collecting duct here. There are probably 1 million glomeruli and 1 million nephrons in each kidney. Maybe there's like 100,000 collecting ducts or so. And eventually the collecting ducts are going to go down. They're going to join and make bigger and bigger and bigger ducts. And they terminate at the renal papilla, dripping urine continuously into the renal, out of the renal papilla, I'm losing my mind here, into the minor calyx. What else? What else? With the blood flow, we had the peritubular capillaries, we had the vasa recta. Eventually we get into the cortical radiate or interlobular vein, into the arcuate vein, and an interlobar vein as well. You know what I'm thinking? What would be a great question for an exam, like a lab exam? A tracing question.
That would be good.
Like
really
trace a molecule of water from the abdominal aorta all the way to the toilet, naming every blood vessel and tube through which that water passed.
That would illustrate understanding of the flow.
That would be good. All right. Adios.